So Fermat like worked with numbers of the form. So first of all, these are called Fermat numbers. So he worked with numbers of the form, let's call them Fn, and they're of the form 2 to the 2 to the n plus 1. And this guy started listing these numbers, and he mistakenly believed that all of them are primes. So he started listing these numbers. So there are 3, 5, 17, 257, 6, 5, 5, 3, 7, etc. And he mistakenly believed that all of these numbers are primes. However, Euler pointed out that the number 42967,297 is divisible by 641. And this is 2 to the 32 plus 1. So they're not all primes. So we can't do it like this easily, I guess. So what are we gonna do here? So the beautiful part, even though Fermat's guess was wrong, the numbers he was looking at still give one of the cleanest proofs that there are infinitely many primes. Here's how. Let's make a claim here. We're gonna claim that all the Fn's are coprime. In other words, if you take the GCD of any such two numbers, like the GCD of Fn, Fm, this equals 1 for every m not equals to n. Okay. So before proving this thing for you, I guess let's quickly agree on something. If we prove this claim, then we immediately get that there are infinitely many primes. Of course, because these numbers are bigger than 1, and hence if all of them are coprime, then if you pick any of them, that's gonna have a prime divisor, and that prime divisor can't show up in any of the others, and hence you have an infinite list of numbers, each of which giving rise to a prime that is coprime to all of others, and this kind of finishes what we want. So it suffices to prove that the Fn's are coprime. And to do this, we shall use like a recursive way of defining the Fn's. So here's a proof. So first, the Fn's satisfy the following property: F0 times F1 ... times Fn minus 1 equals Fn minus 2. If we prove this, I claim that we'll be done. So let's call this a subclaim. So it suffices to prove this because let's suppose that k is less than n without loss on generality, and that let's say d divides both fk and fn. So we're trying to study the GCD of fk and fn. So let's look at a common divisor of these. Well, a common divisor of these must necessarily be 1, and here's why. So first things first, fk appears in this list of numbers, or actually appears in this product, and hence necessarily d divides this thing. So d divides this thing. But then we also know that d divides fn, and hence d divides this thing and d divides this thing, and therefore d must divide the difference. So d must divide 2. So d must divide fn minus that product, and therefore D must divide 2, right? And thus D must be 1 or 2. But D can't be 2 because the numbers we're working with here, the FNs, are all odd numbers. So D can't divide Fn if D is 2, right? And hence D must be 1. And therefore the GCD of Fn and Fk is 1. In other words, if we're able to establish this identity over here, then this claim follows immediately, and hence we have infinitely many primes. Okay, so let's see how to prove this this thingy here. How do we prove this thing? Well, that's not too bad. We can just use induction. So let's quickly do it using induction. So the base case is gonna be this is F0 and this is F1. So it's clear that F0 is 3, which is 5 minus 2, and hence it is F1 minus 2. So the identity holds in the base case. This identity holds in the base case. Okay, now let's suppose that F0 dot Fn minus 1 equals Fn minus 2, and let's prove it for n minus 1, n plus 1, excuse me. Let's see. But we have Fn is by definition F2 to the 2 to the n plus 1. And therefore, if I look at Fn minus 2, that is 2 to the n minus 1. Therefore, if I take this identity and multiply it by Fn, here's what happens. So if I go ahead and multiply this identity by Fn, so this is Fn minus 1, and then I multiply by Fn, the right hand side is going to be Fn minus 2 times Fn. And the product of these two can be easily computed because it's just difference of squares identity. And we get that this is 2 to the n to the 2 minus 1, which is 2 to the 2n plus 1 minus 1, which is, of course, 2 to the 2 to the n plus 1 plus 1 minus 2, and this thing is Fn plus 1, and this thing is exactly the identity we're looking for. It's precisely this thing at n plus 1. Okay? So this gives a beautiful proof because the way Euclid's proof is built is that usually you start with a finite list of primes and you're like, this finite list of primes can't cover all of the integers. However, what this is telling you is that I can give you an infinite sequence of numbers, each of which containing a prime that is co-prime to all of the others, that is distinct from all of the others, and hence you have an infinite sequence of primes.